All right, so here we have the read and got it for 4-3. And we'll start out with, so classifying a function as linear or nonlinear. That's pretty straightforward. And we're going to have some story problem fun with this, because you know I love my story problems. The area A in square inches of a pizza is a function of its radius r. That's pretty straightforward, right? In inches. The cost C in dollars of the sauce for a pizza is a function of the weight W in ounces of sauce used. Graph these functions shown by the table below. Is each function linear or nonlinear? So that's the easiest way to tell. And if you graph the pizza area here, right? Radius is 2. That's the area. You know, the whole pi r squared thing, right? Radius is 4. There's your area. And it becomes pretty evident pretty quickly. This thing is not. So if I look here, this is going up by 2s. This is going up way faster than that. And not just a multiplying factor, right? I mean, it's a multiplying factor, I guess, but the squaring is what really does it. And if you graph that, you can see down here, obviously it's 0, 0, right? 2, 12.57, and you can just see how it grows. It's a curve, not a line. Again, it's a curve, not a line. Sauce, the weight, 2 ounces, right? The cost is 80 cents. 4 ounces, 160. 6, 240. That's just straight up multiplication. Obviously, 40 cents an ounce. Going to make a nice straight line. So both are functions. This one is not a line. This one is. So the question on the got it here, table below shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. Kind of fun, right? Cutting in half. Graph the function represented by the table. Is the function linear or nonlinear? So number of cuts, 1. So 0 cuts, you had a whole sheet of paper, right? So if you want to start the table out with, start the table out with 0 and 1, right? Fraction remaining. But instead here, 1 cut, 1 half. 2 cuts, you have a fourth left. 3 cuts, an eighth. 4 cuts, a 16th. And if you go to graph that, we can see right here when we do that, that it is clearly not a line. Now it's, this is not going to be continuous either. It's going to be discrete by our definition, right? Because you have literally pieces left, not fractions of those pieces or something else, fraction of a fraction, however you want to look at it. And will the area A in part ever reach 0? And explain. Well, technically no, right? You can always multiply by a number, by 1/2 each time. The denominator of the fraction will get larger and larger, so the value of it will approach 0, but never quite reach it. Eventually, your scissors won't be able to cut it. So it'll approach 0, but never quite reach it. Problem 2, representing a pattern and nonlinear functions. So again, more of that pattern piece, understanding that functions are starting out really as just patterns. The table shows the total number of blocks in each figure below as a function of the number of blocks on one edge. So again, total blocks as a function of one edge. One edge, you have 1 block. 2 edges, you have 8 blocks. 3 edges, you have 27 blocks. And we can see that here, that pattern. And obviously an ordered pair. What is a pattern you can use to complete the table? Give you a hint. You're going to want to start thinking about squares and cubes of some of these. Obviously this one's cubed, and the word, notice it's making a cube, and the word cubed for being to the power of 3 is not just from nowhere, right? Literally it means cubed, a cube. So it's pretty easy to come up with that. So when I ask you to look for the pattern, start thinking about squares and cubes in these nonlinear functions. It happens pretty quickly. So in words, the total number of blocks in the cube is the cube of the number, rather, of blocks on one edge. So cubed, y is x cubed, right? 1 cubed is 1. 2 cubed is 8. 3 cubed is 27, right? 3 times 3 times 3, so on and so forth. And you can graph that and see that it's clearly not a line. It's going to grow rather quickly. And notice here, again, a discrete function, right? The graph is discrete. Alrighty. The table shows the number of new branches in each figure of the pattern below. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. So if I have 1, right, there's 3 branches sticking off. Now from those 3, right, so figure 2, each one of those branches off into 3. Figure 3, each of those branches off into 3. So our pattern here, and this could be a tree, I don't know what it's really representing here, but 1, 3, 2, 9, 3, 27. So you got to look what comes next. You have to find the pattern. And you can see I have that shared with you down below here. I'm going to share that with you down below. This one's kind of fun. Instead of being something cubed that you might have tried, we take 3 and it goes to the x power. So whatever x is, right, whatever my input is, that becomes the power. So obviously we're going to go with 81, 243. And when you go to graph that again, it's going to be a growth. So it's going to be nonlinear. Hopefully you got that. If you get that on your own, you can kind of see that now. That's something else, another trick we'll try. All right, so continuing, writing rules to describe nonlinear functions. I have this ordered pair, or this set of ordered pairs, I should say, represents a function. What is a rule that represents that function? So you can, again, we talked about before, putting that in table format. It might help you to see it. And I don't want to steal these from you. You can always obviously check the answers, but try to work on them on your own without that. See what your brain comes up with. It's kind of fun. It's one of those, problem-solving activities. So again, so things to think about. You can see the words here. What rule produces 2 given a value of 1? Well, you can double it, right? You can add 2 to the x power. Those are things you can try. So try it on the next one. Does 2 plus 1 get you to 4? Well, no. Does doubling it, right? Does it work for each of these? Does 2 to the x work for all 3 pairs? And keep trying it till you find one that works. So those are things to give a go at. Look for those patterns. All right, so here, again, looking for a pattern. This one becomes pretty clear pretty quick that, adding something's not going to work, right? Because 1, you don't really add anything. You can add 0, but that's not going to get you anywhere. Doubling it, right? No, that works here, but it didn't work here, right? Tripling it worked here, but not here and here. So what we find after maybe trial and error is that squaring it works. You can try cubing, try squaring, all different number of things. And again, I don't want to steal that from you. I want you looking those up, or don't want you just looking at the answer. See what your brain comes up with. Give it a try.